Okay, so to rehash some of the stuff because I forgot to start the recording, let's just hit those exam statistics real quick. The high score was 100%. There were a few of those. Low score was 51%. The mean was 79, which I think is about where it should be. The elapsed time was 41 minutes, mean elapsed time. I do know there were some people who didn't have enough time to finish and left questions blank. There were also people who got very close to the deadline, so I know they were rushing at the end. I will take that into account on the next exam. There's a survey, so that's the place to do that. You can find that from the announcements. Please take that survey. Again, very quickly, people mostly struggled with math. That was the most, for the 10 people who took the survey, math was the biggest struggle. I'll try to find more recommended YouTube videos, but if you look up Crash Course Chemistry on YouTube, there's a playlist by Hank Green, and he's got like 47 videos, and those are good. I'm going to work through more formula/math problems, so at the end of each lecture now, I'll start adding in the even questions from the homework, and we'll go over some of those. Yes, and I do want to add more time for the next exam, but the time limit's there, so it makes it harder to cheat. It's just kind of what you have to do for online exams like this, especially when everybody's taking it whenever they want throughout the day. I will try to highlight what's going to be on exams. The hard thing is there's always a little bit of everything on the exams. So the questions that are on the exam are then, they're going to be different than the homework a little bit. They're going to be different from the practice tests a little bit, which if you didn't know, there's practice tests for each chapter. And you should do those. But the idea is that the questions are different enough but cover the same concept, so that if you know the concept, you'll be able to do the question. Okay, I think we're caught up now. So the lecture slides are available beforehand. I wanted to do this just in case people aren't familiar with Canvas. Just a little bit of a walkthrough here. So let's see. Right, so this is, that's my view. But if we go to the student view, right, when you go into the class, this is what you see. The first thing you should do is go to the course modules. And when you go to the course modules, right, you've got all these different things. If you look at like chapter 3, preview for chapter 3 has all of the learning objectives. So if you're looking for something to study for these learning objectives. This is just some advice. Read it, watch it, read it again. So if you're watching the live lectures, right, read some of the section or the keywords like I said before. Then do the lecture and then read through that chapter again, at least skim through it. Because it's going to make a lot more sense the second time. And then I have down here the materials and the assignments for this chapter. The materials includes the PowerPoint slides. So you can click on these and you can download the PowerPoint slides ahead of time. And if you click on PowerPoint handouts, there's a black and white version. So if you wanted to print this and then take notes along with the lecture, you can do that as well. And then there's also, if we go back to modules, right, there's this practice test. So if you work through this, maybe don't do the practice test right away, but you can come back here and take this quiz. There's 25 questions there for you to study, or for you to test your knowledge of your studying. And again, this is just sort of like, these are the things to turn in, review the chapter, and then you can take that quiz. It's not graded, and right, if you cheat on the quiz, that's not helping you out at all. Okay, so let's see what else was here. I did set up a collaborative Spotify playlist. There's a link on the Discord, and it was in the announcement for the grades being released. So you can go in there, add that playlist, and you can add your music to that playlist. And then I'll shuffle that at the beginning of class. Lastly, for the things that I can sort of change or do something about, a lot of people struggle with sig figs and formulas and math in general, the class as a whole. Just please ask me questions. Come to, I have the office hours set up now, 2 to 3, 8 to 9. Um, I'm also kind of at my computer all day, so if you send me a message, I can respond quickly. I'll probably respond very quickly. Um, I'm not going to think that you're dumb or that, you know, you're not getting it because you're not trying or any of these things. I'm not going to judge you for asking for help because that's why I'm here and that's why I'm asking you to ask me for help. Um, this class comes at a breakneck pace, and that's just the nature of the beast in terms of that. But ask questions, ask other people, um, post questions on the Discord. But make sure you ping me on the Discord. If you don't ping me, I won't see the notification. Okay, there's some things that I cannot change about the course. One of those being the amount of homework. There's a lot of homework, but you got to remember that homework is studying. These are problems that are given to you that are just studying. And every one of those problems you do is reinforcing those concepts. So there's no reason to cheat on them, but treat them like they're studying. The homework due dates. The homework due dates are there because I know there are probably many of you out there who are like me, and if I don't have due dates, I won't do it until the last minute. And then, if you've had a week of assignments in this class, that means you've got 4 chapters worth of material and problems that you have to do in a single day. And that's not helping you learn it to do it that way. If you would like to do it differently, if you think, I don't need these deadlines, I suppose you could send me a message and I can change those deadlines. But I'm very hesitant to do that. Because this is another, wrote this down beforehand, but I'm actually giving you more time than other instructors would. There are some 4-week summer classes where they will give you just 1 day to do the assignment. So I'm giving you until midnight of the next day to do the assignment, or both assignments really. So don't wait till the last minute. There's no room for procrastinating in this class. If you fall behind, unless you put out a Herculean effort, you will stay behind. Somebody asked for study guides. I would use, again, those course outlines as a study guide. I would use the practice tests as your study guide. I believe there's no limit on how often or how many times you can take those practice tests. It's unlimited attempts. So you can take those as many times as you want. You could copy those questions out, write them down, and study those. Another thing I would do to study for this class is categorize things. Right? So look at the periodic table, look at the lecture slides, and start writing down. And we've covered these in class too, right? Like heterogeneous, homogeneous. Create your own definition for those. If you can redefine those in your own terms and use that definition, on the practice test or on the homeworks, that is going to really help you solidify in your mind what those are. Somebody said that the lectures are long and boring. Sorry about it, I guess. There's not a whole lot I can do about that. We got to cover an entire chapter every day. They are going to be long. Okay, switch to the iPad here. There's actually one more thing. Okay, so I did do this. I wrote down some of these equations. These are sort of the equations we've covered so far. I think I got all of them. Let me know if I didn't. But we have density. Let's see, I'll just mark it over here, right? We have density, right? So it's mass over volume. Mass can be it's usually in grams per centimeter cubed or grams per milliliter. It can have other units, but it's unit mass per unit volume. And so then we also have our sort of our heat equation. So when something changes temperature, and those are in units of heat energy in joules, and then we have the mass, heat capacity, and change in temperature. I know this was another question on the exam that people had a hard time with. matching those up. We also have an equation for atomic mass. So we want to know the atomic mass of something. Then there is, use the atomic number. I think there was some confusion with that. And the number of neutrons. You could just add those together. And then we have average atomic mass. So if we consider all of the isotopes that exist in nature, then you take the atomic mass. Oh, that's the unit I should have used. Atomic mass of, let me change this real quick. Use the atomic mass of isotope 1, the atomic mass of isotope 2, and then you're multiplying this atomic mass by its percent abundance in nature as a decimal. And that can go on for however many isotopes there are. And then we have ion charge. So to calculate the charge of an ion, it's the number of protons, right, which is the same as the atomic number, minus the number of electrons. And so by using this, you can deduce sometimes, so let's say we have aluminum, right? If we have aluminum with a 0 charge, set up this is new, add the periodic table here. So if we look at aluminum, it's in group 13 there, which if you remember is also 3A. But aluminum, right, 13, atomic number is 13. Sorry, atomic number is Z. So its atomic number is 13, and since we have 0 charge, which would normally be written, right, wouldn't be written. If there's no charge, it's implied it's 0. So if our atomic charge is 13, if our atomic number is 13, we have 13 protons. And that means we have this is also a, right, positive 13 charge. But if aluminum has no charge, that has to be canceled by 13 electrons. So our total charge, I should say this, right? So this is our equation. Equals our ion charge. Or charge, actually. I should just say charge, because if it's neutral, it's not an ion. Okay. So it can help to make your own sheet like this, right? And this is the kind of like cheat sheet that I was talking about that you can use on the exams, because I have no way of policing it. But do this, write out all of the equations, write out what the units are. And by doing so, you're going to be, putting it into your own mind for what they are. You'll be learning it in process. Okay, were there any other questions? Oh, okay. Then let us move on then. So, just before we get right into this, I wanted to do like I want to talk a little bit about, how far we've come. We learned a lot, especially in chapters 1 and 2, about the scientific process, really about how we write numbers in scientific notation, significant figures, and how to work dimensional analysis. That was like chapters 1 and 2. Then in chapter 3, we learned about, what was chapter 3 exactly? Oh, matter and energy, right? So we learned about matter and energy. We learned about, why molecules and atoms move around the way they do. And then in chapter 4, we were finally introduced to the atom properly. And so we have our atom, and then our atom has some cloud of electrons. You can see that. Our atom is made up of, in the nucleus, from our nucleus, right, we have protons, and we have neutrons. And the charges on those respectively, right, positive for protons, 0 for neutrons. And then this cloud around the nucleus is our electron, or our electrons. And that has a negative charge. And so we talked about then how the number of protons can be used to identify the element. And then we talked about, too, how we can combine atoms into molecules. right? So if we have a bunch of atoms together in a specific ratio, that gives us a molecule. And then we also talked too about, right, how do we group those molecules? How do we classify? If we have a mixture of molecules, it can be heterogeneous or homogeneous. If we have elements by themselves, then those are, or if we have pure compounds, those are either elements or it's an element made up of a single type of molecule. So today we're going to be talking more about molecules and then how we name them. Change this view to single page. Right, so we're all familiar with sugar and salt. I personally love both of those things. Ordinary table sugar is a compound called sucrose. Sucrose is a molecule, and a molecule that contains carbon, hydrogen, and oxygen atoms. And the properties of sucrose are very different from those individual elements by themselves, right? So carbon is what makes up graphite, which is what you use to write your pencil, and tastes nothing like sucrose molecules. Don't ask me how I know that. Hydrogen is a gas, and so is oxygen, and that's, we know that sugar is a solid. So when we combine these things, we get different properties out. In a similar way with salt, on the left here, this is sodium, and over here, this is chlorine. Keep pulling that. You can see that, I'll write this too, chlorine is a gas, and it's this yellow, very, very toxic gas. And sodium is a very reactive metal. It's a soft metal, but it's a very reactive metal. When we combine those two things, though, we get something very different in table salt, which makes potato chips delicious. And so the properties of a compound are, in general, different from the properties of the elements that compose it. I cannot think of an example where that's not the case. Almost always changes pretty drastically. Now, when we look at a compound, it displays a constant composition. So if you're to take a table salt here in the U.S., if you're going to go to Japan, if you're to go to China or Australia, and look at table salt, it's all the same. And most of these substances that we encounter in everyday life are not elements, they're compounds. Free atoms are very rare in nature. And so a compound is a mixture of different elements. In a compound, they come in fixed, definite proportions. Right? So we talked about that. In our pure compounds, if you have a single type of molecule, there's going to be a fixed, definite proportion for the number of oxygen and hydrogen atoms in water, for example, or in table sugar. But if you have a mixture, right, think about if you add salt to water, that's a mixture. And you can add a little bit of salt or you can add a lot of salt, and you still have a mixture. The proportion isn't fixed. It doesn't matter how much salt you add, it's still a mixture. So if we look at, for example, if you filled a balloon with helium, or hydrogen in this case, you're going to have other molecules in there as well. But like adding salt to water, adding helium into a balloon, and then if you were to add some air to that balloon, it doesn't matter what the ratios are. You can change that ratio, it's still a mixture. But when you look at water, the ratio of hydrogen to oxygen atoms is fixed, right? So you can see that by just looking at these pictures. I'm going to zoom in. This is called a space filling model. We'll cover that in a bit. But you can see, right, for every single one of these, this is the oxygen, and this is the hydrogen. And on all of these, we have one oxygen, two hydrogens. One oxygen, two hydrogens. One oxygen, two hydrogens. And it is exactly like this in nature. There's always one oxygen bound to two hydrogens in a water molecule. It was Joseph Proust, way back in the day, who formally stated that the idea of elements combined in fixed proportions to form compounds. And this is called the law of constant composition. So all samples of a given compound have the same proportions of their constituent elements, right? So water here is the same as water everywhere else in the universe, as far as we know. And salt would be the same everywhere in the universe. It's always going to be one sodium, one chlorine stuck together. So when we talk about this, and this harkens all the way back to that first chapter, chapter 1? Yeah, I think it was chapter 1, when we looked at patterns, right? Trying to identify patterns. So if we took an 18-gram sample of water, we would get 16 grams of oxygen and 2 grams of hydrogen. And again, that's a ratio, mass ratio of 8. And this will be true for any water sample, no matter the origin, whether it's here, or it's in the Andromeda galaxy, or it's in some unnamed galaxy billions of light years away. And the compounds have constant composition with respect to mass because they are composed of atoms in fixed ratios, right? Like we saw with water. They're always bound in that same configuration, which is kind of wild if you think about it. So let's look at this. So we have 2 samples of carbon monoxide obtained from different sources, and we decompose them into their constituent elements. One sample, and I'm going to just write this down as we go through. We have sample 1. Produces 4.3 grams of oxygen, 4.3 grams oxygen, and 3.2 grams carbon. Now I wrote them this way on purpose, and you'll see why in a second. So now if we go to sample 2, sample 2, we look at sample 2, we have 7.5 grams of oxygen, and 5.6 grams of carbon. Where'd my calculator go? So are these results consistent with the law of constant composition? And at a glance, it's difficult to tell, right? What do we know about the law of constant composition? That the mass ratio for a sample of carbon monoxide, here or anywhere, should be the same. So when we look for ratios, it's nice to get a whole number. And you know you're going to get a whole number because you put the largest number on top and divide it by the smaller number. So you do 4.3 divided by 3.2. That gives us 1.34 approximately. 7.5 divided by 5.6. And we get also 1.34. There's a slight amount of variation in there. If you did that yourself, you're going to see that, out to a certain number of decimal places, they're different. But that's within experimental error and deviation. So you see that these ratios of grams of oxygen per gram of carbon is the same. So these results are consistent with the law of constant composition. So then we also use a chemical formula, right? So this is kind of the first way that we write out elements. We use a chemical formula to indicate the elements that are present in a compound and the relative number of atoms of each. The relative number of each atom. I don't know why that reads so weird. So subscripts are used to indicate the number of atoms of each element. By convention, a subscript of 1 is omitted. And this is very important. If you put your subscripts too high up, I'm going to mark things wrong because that's not how it's supposed to be written. So for example, water. You can't write H2O like this. You might see that sometimes. Sorry, here's something outside. You might see that sometimes when somebody's typing it, because sometimes there isn't an option to make a subscript. And that is the only time that you might do this. For doing it in your homeworks, if you're typing your homework, you need to find a way to make it a subscript. Right, so 2, and then we're... lost my train of thought here. So, okay, yeah, 2, right? So we have 2 of those, and then since we have 1 oxygen, you can see there's an oxygen there. We don't need to say that there's 1. So we drop that.
Is there a way to make it a subscript on a normal keyboard? I mean, or do we just need to somehow write it in manually?
If you're using Windows, Windows. If you're using Microsoft Word, you can use Control Plus makes it a subscript. Actually, here, let me can show you this real quick. I think. Okay, so if you're in Word, oh, this is super hard to see. Okay, it's tiny, but it's up here in the font section. So let me make this big. Right. So if we want to do H2O, right? I already know that's incorrect, but you can do H, and then there's a button up here. It's an X with a 2 subscript, and you can make that a subscript. Type 2, hit that subscript again, and do O. The other thing you can do is you could type this out first, highlight the 2, and then click the subscript button. Or
Awesome.
the keyboard shortcut is Control plus plus, or Control plus. If you're using something other than Word, you'll have to figure it out. Oh, here we go. Right. Any other questions? A common name or common chemical formulas include sodium chloride, right? So Na is the symbol for sodium, Cl is the symbol for chlorine. We'll figure out why it's chloride instead of chlorine in a bit. But for table salt, including sodium and chlorine atoms, it's a 1-to-1 ratio. And then for carbon dioxide, again, notice we got 2 subscript, carbon dioxide. Again, we'll come back to that later, indicating carbon and oxygen atoms in a 1-to-2 ratio. And then for table sugar, indicating carbon, hydrogen, and oxygen atoms in a 12 to 22 to 11 ratio. You can see those match up with these. So the subscripts in a chemical formula are part of the compound's definition. So if you change the number, you change the compound. Again, just using water as an example, right? If we had H2O, if you add this H2O2, this is hydrogen peroxide. And if you drink that, it will kill you. You can rinse your mouth with it, but don't drink it. There's a joke that goes, 2 chemists walk into the bar, and the first one orders H2O, the second one orders H2O2 and dies because he was served hydrogen peroxide. So if you change these subscripts, it changes the compound. It's something completely different. And the example we're given here too is that CO is the formula for carbon monoxide, which is an air pollutant. You should also have a carbon monoxide monitor in your home or apartment. And CO2 is the chemical formula for carbon dioxide, which is a relatively harmless product of combustion in human respiration. So when we write out chemical formulas, we write the most metallic element first. That's why I put together this, so we can have this periodic table, although I can't write on it. But going from right to left, we get more metallic. Right? So things like lithium and beryllium in groups 1 and 2 are going to be more metallic than boron in group 3, carbon, nitrogen, oxygen, and so on. So when we write something out, we see that nitrogen, N, is to the left of oxygen. So we write nitrogen first, which is an example of a something with a something without a metal, the more metal-like element.
Does this always hold true? And what about the helium up there? What do these colors represent?
Oh, the colors on this one represent. So hydrogen and helium are kind of weird because they're so small. The colors are representing something that we're actually not going to cover. We cover later. can't write on that periodic table. So in the red, these are s orbital, have an s orbital as their valence electrons. Yellow has a p orbital as its valence electrons, and blue has a d orbital as its valence electrons, while green has f as its valence electrons. Which is, yeah. So this is just, I grabbed a simple periodic table. I think that's what those colors are representing.
Okay, so then when we're writing formulas, it's always going to be left to right.
When you're
There's no
doing,
exception as far as like, I don't know, rhodium would never come before scandium or something. Like,
yeah. I don't think there's an exception. I was trying
okay.
to think. We'll cover some other stuff later, because even when we talk about acids, hydrogen goes first. So if we have, getting a little bit of ahead of it, but we'll just real quick.
Yeah,
If you had
yeah,
something
no
like
worries. I,
hydrogen
I was just
bromide,
thinking that's why I was asking because it seems a little bit confusing further down in the chapter. So we can wait till we get there.
yeah, and we'll observe. So yeah, keep an eye on that, and we'll see if we come up with any exceptions to that rule.
Okay.
I think for the purposes of this class especially, I think that holds true. Um, yeah, because even yeah, we'll talk about oxyanions, but okay, right. So you always write the more metal-like element first, whether it's a metal or not. Again, nitrogen comes before oxygen. Nitrogen would come before fluorine, so on. So the specific order for listing non-metal elements in a chemical formula is shown right here in table 5.1. Oh, here. So there are a few historical exceptions, which the most metallic element is named first. I think that's supposed to be not named first, such as the hydroxide ion. So that is one exception, right? You would write it as OH minus, not HO minus. Okay, so let's practice with writing some of these chemical formulas.
Yeah.
So I
So
kind
that
of
was
kept
that was an exception then, right? Because you're writing
yes,
OH instead of HO. So
yes, yeah. That is an exception to that rule. We'll see if we come up with any others. Don't think there are. I really don't. Um, okay, so let's write these chemical formulas. So we have 2 silver atoms for every sulfur atom. And I'm gonna go real slow so that you can take the time to try and figure this out too. So 2 silver and 1 sulfur, and the symbol for silver, right, Ag, and sulfur is S, and so then for silver, 2 is the subscript. All right, we've written the most metallic metal, the most metallic element first. Again, when we come to nitrogen and oxygen atoms, we just mentioned this one. So the symbol for nitrogen being N, oxygen atom being O, and then we have 2, right? So that's our subscript. For the compound containing 2 iron atoms, to every 3 oxygen atoms, iron is Fe, and oxygen is O, and it's just 2 and 3. Pretty simple stuff so far. So now we also have these things that are called polyatomic ions, and these are groups of atoms that act as a unit, and you do have to memorize them. They all have a similar structure for the most part. Um, so we have 2 or more of the same kind of polyatomic ion. We set off their formula with a parentheses, right? And so this is just saying that we have 1 manganese, or sorry, 1 magnesium, and then we've got NO3, and then we have another NO3. So we have this, let me zoom, right? Because this is indicating that it's this group times 2. So if we were to calculate then the number of nitrogen atoms present in this compound, right, we would do 2 2, that's a terrible, it's so hard to see the yellow. We do 2 times 1, because there's no subscript, so it's implied that it's 1. And we would say that there are 2 nitrogen atoms. And then if we wanted to say count the number of oxygen atoms, it would be 2 times oxygen subscript 3. And so we would have 6 oxygen atoms. And then because magnesium is outside of the parentheses, there's 1 magnesium. Okay, so nitrate is one of those polyatomic ions that you have to keep an eye out for. Most of the polyatomic ions that I can think of are going to be this same format as the sulfate here. So this is sulfate, and you're going to have a nonmetal plus some number of oxygens. Those are your polyatomic ions. That doesn't mean that not every nonmetal bound with a number of oxygens is a polyatomic ion, but generally that's the case. So let's count the total number of each type of atom, right? So we have K, and again, as extra practice, potassium. And we have S, which is sulfur. And we have O, oxygen. So the subscript, right, again, the subscript to the right of the element is the number of that element in the compound. So we have 2 potassium, we have 1 sulfur because there's no subscript, and then we have 4 oxygens. And then when we have multiple, so we got aluminum, right, Al. We have sulfur again, and we have oxygen again. Now, here we have an example of a polyatomic ion. So how many sulfurs do we have? We look at 3. Look at our 3 here, right, for the parentheses. And we say that we have 3 times 1. So we have 3 sulfurs. And we have 3 times 4 for oxygen. We have 12 oxygen atoms. So we have a few different types of chemical formulas. Today we're pretty much just going to be talking about molecular formulas. But you should write these definitions down, right? This is the exactly the kind of thing that I would put on a test, right? We'd have another matching, maybe, and you would have 3 definitions, and then you have to match them to the term that's appropriate. So for empirical formula, it's the relative number of atoms of each element in a compound. For a molecular formula, it's the actual number of atoms of each element in a compound. And then the structural formula, which is more of a diagram of what the molecule looks like. So we use it to represent bonds and show how the atoms in a molecule are connected to each other. For example, if you were to do water, right, oxygen bound to hydrogen and then to another hydrogen. So similar to your molecular formula, it's going to show you exactly how many of each atom, but it's drawn out as a diagram. For our molecular models, we have three-dimensional representations of models, and we use those to represent the compounds. We have a ball and stick model, which represents atoms as balls, and these are the colors on the right that are conventionally used for each atom. And then we have space-filling models. And the space-filling model is our most accurate sort of cartoon representation of what the molecule might appear like if we were to scale it up to human size. So you have some examples of those here. The molecular formula, right? So our molecular formula is the actual number of atoms of each element. Then we have our structural formula, right, which is the diagram just sort of a diagram of how they're bonded together. And then we have our ball and stick, where the ball and stick model now has sort of a 3D element to it. You can see that this hydrogen atom is kind of pointed away from us. This hydrogen atom is maybe in the plane, whereas this hydrogen atom is coming out towards us. So it's a 3D, really gives us the full 3D representation. And then if you look at the space filling model, you can see the similarities between the ball and stick and the space filling, right? The hydrogens are in the same places, but now they're fat, they're huge, right? So they take up all of that space. And that space, right, if you remember back, always trying to rehash these concepts, that the electrons are taking up, and the nucleus is in the center of that. So we often use images to help us visualize connection between the world around us and the world of atoms and molecules. Again, something like this sort of molecular diagram of how the molecules are bumping and shifting around inside of the water. And we talk about these in sort of three different realms. There's the macroscopic world, or what I often just refer to as human scale. Then there's the atomic and molecular world, which are the particles that compose matter. And then there's a symbolic way that we represent the chemicals or particles. And that is our... Oh, I'm sorry, I've left this on. Let me switch back to this. Symbolic way that we represent them using molecular formulas. So this is really our table from before, or our flowchart from before, when we're talking about pure substances. So if we have just a single element, right, those are elements, and then you can have either the atomic elements, like neon here, or you can have molecular elements, so oxygen, and I've hinted at this a few times. And we'll talk about this in a little bit. There's a set of elements that form what are called diatoms, or they're called diatomic because they bond together, so you get two oxygen atoms. Then we also have pure substances that are compounds. So you can have a molecular compound, where they're bound together using what are called covalent bonds. But then we also have ionic compounds. Salt is an example of an ionic compound, and those are, salt is crystalline. Those are sometimes crystalline. Right, so this is what I was talking about, where we have these atomic elements, and then we also have these molecular elements. So they exist as diatomic molecules.
And an ionic compound is what? It has the an extra electron, or
Oh, we'll talk about that. So they're formed from usually two ions. So for sodium chloride, we have a sodium plus, and that's bound to a chlorine minus. And so it is their opposite charges that stick them together.
Okay.
We're going to talk about two different ways that you can memorize these diatomic molecules. The one that I like to use is Brinkelhoff. So it's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Brinkelhoff. And those are all of the diatomic molecules. Just another look at the difference between atomic versus molecular elements, right? So even though that these are all they're all bound together, it's different than something like chlorine, where you have them as two chlorine atoms are actually bound together, instead of in something like lead or mercury or another solid, like any solid element. Those mercury atoms are just close and stuck around each other, but especially in the mercury, right, they can move around each other. They're not bound, they're not chemically bound together. In a chlorine molecule, these two are chemically bound. So this is the other acronym, or acronym that you can use to remember these elements that are diatomic. Right? So we have hydrogen, and then nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Horses, I'll use the pointer for this. Horses need oats for clear brown eyes. So whichever one helps you remember them better, it's just whatever one works for you. So this is where we're talking about molecular versus ionic compounds, right? So generally molecular compounds are formed from two or more nonmetals, whereas ionic compounds contain one or more cations paired with one or more anions, and usually they contain a metal. So it's always a molecular compound if it's two or more nonmetals. If there's a metal, it's an ionic compound. But there are some situations where you can have, I can't think of a situation at the moment, but you can have ionic compounds formed from nonmetals as well. Usually, though, contain a metal. So, for example, here, sodium chloride, this is ionic, and this would be molecular. For carbon dioxide. So we have ionic compounds, right? We've got a metal and a nonmetal, that's ionic. And the basic unit of ionic compounds is the formula unit. Because unlike molecular compounds, ionic compounds do not contain individual molecules, but they're rather a grid in a three-dimensional array of alternating cations and anions. So, for example, sodium chloride, right, is not just individual molecules of sodium and chlorine. It would be more like sodium and then chlorine and then sodium and then chlorine's over here. So they exist in this grid. So we call a formula unit just one of these individual pieces. So the simplest whole number ratio. So let's take a look at these and classify each as an atomic element, molecular compound, or ionic compound. So chlorine. Would chlorine be an element or atomic, molecular compound, or ionic compound?
Atomic element.
Sorry, what was that?
Is it atomic element?
Chlorine is one of our Brinkelhoff.
Oh, gee, so diatomic molecule.
Mm-hmm.
Oh, this is confusing.
Is a little confusing, and this is why I think flowcharts are super necessary, because if you can come up with a way in your mind to go through stepwise, like, okay, if it's Brinkelhoff, it's not an atomic element, right? And then you can move from there. So you got to check first if it's one of the Brinkelhoff elements, and then see, is it and then you'll know if it's a molecular compound or a atomic element. Sorry. A molecular element. It's a molecular element.
So the Brinkelhoff stuff is molecular elements?
Yes. Yeah, these are the molecular elements. So really you would start, your flowchart would probably start, are there multiple elements in this, whatever it is, right? And then you have yes or you have no. So if we have multiple things, then we would say yes, and then it can be either a molecular compound or ionic compound. And then you would ask, your next question would be, well, you would know it's a compound, And so once you know it's a compound, your next question would be something like, is there a metal? Because if we have a metal, if our answer is yes, then it's ionic. If it's no, I think we might have to come to some other. It's hard because there's a lot of nuance that goes on beyond general chemistry, right? So one of the difficulties is figuring out where the limit is for general chemistry. So I think for this class, if there's not a metal, then it's almost definitely a molecular compound. But you can see though how, each of these, to be each of these four things, you have to exclude other things. And so if you we have a tree, there's a tree at the end of this decision tree, right? If you can make a decision tree or a flow chart, that's going to help you a lot with identifying these quickly. Not just to have it as a cheat sheet, but by creating it, you're going to absorb some of that information, right? So let's kind of use our flow chart that we've made now so far, and look at our next compound, or our next element, or whatever it might be. But we do have multiple elements, right? So since we have multiple elements, we can select yes, and we can say it's a compound. And do we have a metal? If you remember, metals are basically the entire left half of the periodic table. This doesn't have the diagonal line on it, but if you go from boron to silicon to arsenic, tellurium, down that way, that's sort of the non-metal, or those are the metalloids. But we can see that nitrogen and oxygen are well and truly inside of the non-metal region. So we know they're both nonmetals, so this would be a molecular compound. Okay, so our next element here, take a second to find it on the periodic table if you don't already know what it is. But we can start with our flow chart. Do we have multiple elements? No, we've got just one. So when we answer no, now we're either looking for a atomic element or molecular element. And basically that decision tree is, is it Brinkelhoff?
No. That means it's atomic.
Yep. So if we answer no, then it's atomic. Sorry, my handwriting's getting real messy here. So then we have an atomic element. All right. Now we can move on to the next one. Do we have multiple elements? Yes, we've got Na, which is sodium, and we have oxygen. So we can move down our yes, and we can say we have a compound, but what kind of compound do we have? Do we have a metal? We'll look at our periodic table. We find sodium is on the very left side of the periodic table, so we know that's a metal. So we could say yes, and we have an ionic. Ionic compound. And then again, you can just repeat this same process. And so this is why I think I've mentioned a few times before, make a flowchart. This is what I mean, right? And you can see how useful this is and how quickly you're going to work through these problems if you have this kind of thing to refer to. And every time you go through it, you're reinforcing those pathways. And really what you're doing is you're reinforcing the image of this table in your mind. And so you can go through that flowchart then later on and probably don't even have to look at it. So again,
are transition metals, like in this formula, are transition metals still considered metals?
Yes.
Okay, so all of those in blue, and then when you have that line, that little zigzag line,
Hmm.
everything under there is still considered a metal.
Yeah, I think I would use the periodic table from your book, and that's going to highlight which ones are metalloids, because that's like the gray line, or
Yeah.
that's the gray area.
Okay.
Um, but the questions for the most part, on the exam and stuff, will be using
Ones that are
metals.
more
Like that's
obvious.
not the point. The point is not to confuse you.
Okay.
Uh, you have another question?
No.
Oh, okay. All right, so we can move on. So yeah, so again, um, let me pick up the pace a little bit here because we're already an hour in. Actually, no, we're doing fine. We're 28 slides. So chromium and so Cr, chromium, gave it away, and chlorine. So if we have multiple, yes, then we have a compound. Compound. Do we have a metal? If we look at our
Yes.
periodic table,
Chromium.
chromium's
Yes.
in the blue,
Yeah.
right? Why can't I see it right now?
It's underneath number 6. Chromium 24.
Oh, 24. Wow. Just could not find it. Anyways, chromium there, yeah, in the blue. We knew it was over there. I just wanted to find it. And then we have chlorine. So we have a metal, yes. So we're ionic compound.
Can you do you still want that periodic table there, or on the bottom right of the screen?
Thank you. Thank you. No, I don't. Okay, so when we write formulas for ionic compounds, right? So when we want to write these out, um, we can use the ions with predictable charges. I guess I did want it there. So we have our ions with predictable charges. And again, remember, I should have done a better job picking this periodic table. But 1 and 2 are 1A and 2A. 13 is 3A. Yeah, I don't have a way I can change it right now. Not quickly. But so when we look at our ions with predictable charges, those are 1A, 2A, and 3A. They form +1, +2, and +3 ions. So something like zinc. Uh, zinc is sort of a special case. It's outside of that, but it only forms a single charge. And so is silver. Only forms a single charge. So those are the ones outside of those three groups that you should remember. And then for nonmetals, it's the group number -8, or you count back from group 8. So if we were to look at like 17, if you look at column 17, that's also 7A, as we've been calling it. So fluorine, chlorine, bromine, iodine, even acetine, those will all form -1 charges. And then everything in 16, right, which is also 6A, is going to be oxygen, sulfur, selenium, tellurium. Those all form -2 charges, right? So it's 8 minus the group number. Or the group number -8, because they all form negative charges. So we're going to do, this is an example, something from 6A -8. We can ignore this A, and we'll get a -2 charge. If we were to do something from column 7, or 7A, -8 would be a -1 charge. We did cover that in chapter 4. So ionic compounds always contain positive and negative ions. That's why they're ionic. In the chemical formula, the sum of the positive charges must always equal the sum of the negative charges. And this actually helps us. We'll talk about the crisscross method just now. So I'm going to close this again. So we can write the symbol for both ions, including their charges, and then we make the magnitude of the charge with each ion, without the sign, become the subscript for the other ion. This is called the crisscross method. And this is the easiest way to do it. And then if possible, reduce the subscripts to give a ratio with the smallest whole numbers. And then you want to check to make sure that the sum of the charges of the cations, Those are the positively charged. Exactly cancels the sum of the charges of the anions. I'll actually write the charges like this. So that might be a little bit confusing, but we'll do an example. Again, grabbing our periodic table. So we have strontium and we have chlorine. So take a second, try and find strontium yourself on the periodic table, but we don't want to take too much time. So strontium is Sr, and that is in group 2A. And then we have chlorine, and chlorine is all the way on the right side in group 7A. So as we learned, in the previous couple slides, everything in 1A, so 1A makes 1A is +1, 2A is +2, and 3A is +3, right? So we have strontium is in 2A. So we're going to say that strontium for this ionic compound is going to form a 2+ ion. And then chlorine, we looked at 6A, right, is a -1 charge, and 7A is a -2 charge. This would be a good thing to, jot down or just, memorize. So we know that chlorine is in, I did this backwards, I am so sorry. 7A forms a -1, 6A forms a -2. So chlorine is in 17 or 7A, so it's a -1 charge, right? And we leave off the 1. So the crisscross method, we then take the 2+, and we put that over here as the subscript for chlorine. We take the 1-, and without the charge, we're going to make that the subscript for strontium. So we'll end up with Sr, and I'm just going to write this for the sake of clarity, the 1, Sr1, Cl2. And so your final answer should be SrCl2. And so whenever there's charges like that, so we can also do something like, let us do Al. Actually, let me check that this isn't an example. Okay, it's the example in the next one. Is it? Okay. All right. So this would be your answer. Okay. So then, moving on here, we have a compound that forms from aluminum and nitrogen. Yeah, this is exactly what I was about to do. Okay. So we have aluminum. All right. Symbol Al. And we know that that's in group 3A from our periodic table. So again, 3A forms a +3 charge, so we can write 3+. And then for nitrogen, nitrogen is in 15 or 5A. And so I guess I didn't say this exactly, but from that formula before, we can find the charge as the right, its number, or its group number, should be 5A. -8 will give us 3. Sorry, -3. So nitrogen is going to have a 3- charge. So again, if we use their crisscross method, we take aluminum's charge, remove the plus, and put it as the subscript for nitrogen. Take nitrogen's charge, remove the minus, and put it as the subscript for aluminum. So we'll get aluminum 3, nitrogen 3. And here, you'll notice that both of them are 3. And we talked about when we use formulas for ionic compounds, we use what's called a formula unit. So we want the simplest whole number combination that we can make. And so since we have 3 of each of them, we can divide by 3 and say our formula unit then would be ALN.
When do you put the charge on the top right versus the bottom right?
The charge on the bottom right?
Well, so I noticed on your when you first started, you have Al and then 3 plus on the top right of the symbol, and then N 3 minus on the top right of the symbol. But then right below it, you've got Al3 on the bottom right, and
Oh,
3 bottom right.
this is down here. This is not the charge.
Oh, it's how many atoms you have.
Yes. Yeah, yeah. So and then on this one previously too, yeah, this is not the charge on strontium or chlorine. Um, this is the number of each atom.
Okay.
Yeah. You can use those charges, and you'll see too that okay. So if we do this now, and we say so we have aluminum, right? Has a 3 plus. So if we have three aluminum atoms, each with 3 plus, and then we add that to each of our nitrogens. So 3 nitrogens here, each with a negative 3. Actually, let me rewrite this too. So this is a positive 3, right? Positive 3 charge. And then 3 nitrogens, each with a negative 3 charge. What we'll get is positive 9 plus a negative 9. And so our resulting charge is 0. And so this is kind of this crisscross method is a is a shortcut to get to that 0 charge that we want. The example that I was going to show earlier is if, let's say we did aluminum and oxygen. So in this case with aluminum and nitrogen, right, we ended up removing those 3's to get to our formula unit. I should write that down here too, formula unit. Right, simplest whole number ratio. We have aluminum and oxygen. Again, aluminum's in 3A, so it's a 3 plus charge. Oxygen is in 6A, and again, using this this formula here, we can say 6 minus 8 is a negative 2 charge. So now when we do our crisscross method, we're going to take the 2 from the oxygen and use it as the subscript for aluminum. Take the 3 from aluminum and use that as the subscript for oxygen. And our intermediate here then is Al2O3.
Okay.
And so if we were to do again like we did with nitrogen, the aluminum nitride, so the aluminum and nitrogen, we can say that we have 2 aluminum atoms, each with a plus 2 charge, each with a plus 3 charge, plus 3 oxygen atoms, each with a negative 3 charge. So when we multiply...
Negative 2 charge.
Negative 2 charge. Yeah. So when we multiply this, we get a positive 6 plus a negative 6. And that's one of our requirements. So this would equal 0 then. And one of our requirements when we write these ionic formula units or ionic compounds is that there's a 0 overall charge for the compound. Just to follow the same format, right? I did the intermediate in red, and then we check to see if we need to reduce it, but we can't reduce aluminum. We can't reduce 2 and 3, so we just keep the 2 and the 3. All good?
Yep.
Cool. Much more to cover. So, these are some of the polyatomic ions. And I think I mentioned earlier that a lot of them have oxygen, and you can look at that below here, right? Almost all of these have oxygen. There are a few exceptions, namely ammonium and cyanide. Some things have more than just oxygen, like acetate. It is, for the most part, memorize those tables. Memorize those ions. Or you can just look them up. And I think there might be a table of some the more common ones that are going to be used, for questions and stuff. I would pay attention to which polyatomic ions are being used in the homework problems, because those are some of the more common ones that are used for these questions. So we can have ionic compounds too that form with these polyatomic ions. So good, we still have the periodic table up. I guess I should have, was that blocking anything here? No, okay. Calcium and nitrate, so we have calcium over there in the 2A. All right, so we have 2A. And then we have nitrate. So you can go back and look up what nitrate is. It's NO3, NO3 minus.
So that's meaning minus one charge.
Correct. NO3 minus, that being a -1 charge.
Okay.
So calcium then, yeah, we know it's in 2A, so it has a 2 plus charge. So again, just use our crisscross method. Take this guy, do this in red again, move it over here, take this, move it over there. And so we'll get CaNO3. But remember, when we have a polyatomic ion, and we need multiple polyatomic ions, we put this in parentheses, and we put the 2 on the outside of those parentheses.
Okay.
To show that there's 2 of this group. You wouldn't write CaN2O6 because, like we talked about before too, if you N2O6 is not the same as NO3. It's a different molecule altogether. Okay. So do another one of these. If you have aluminum, just looked at aluminum, probably the most common element that we'll talk about out of 3A. Right, so it's in 3A. We know then it has a 3 plus. And then phosphate, I'm just going to write this down because I know it. PO4, ooh, actually, I think the charge is 3. PO4 3 minus. Just pulled from the table. So then if we look at, again, our crisscross method, 3, 3, crisscross, everybody clap your hands, and aluminum, 3, and again, remember, we have polyatomic ion, so it's PO4, 3. Oh, should have done this in red because, right, we can take this. This is not a formula unit. Why is it not a formula unit? Not a formula unit. Maybe won't be that bold about it. Red, because we need to simplify it. AlPO4. Do another one of these. So we have sodium. Okay, so find sodium on the periodic table. Na, and it is in group 1A. So we know it has a +1 charge. And then sulfite. So this is again something that's going to come later. This is sulfate, and we remove one oxygen. We change that name to sulfite. So sulfite has 3 oxygens, but the charge remains the same, and that's a 2 minus charge. I'm just going to double check. Yep, 2 minus. SO3 2 minus charge. So again, crisscross method. Oops. Plus there being a 1, right? And then 2. So that we're going to get Na2SO3. We can look at this and see that that is a formula unit. We can't simplify it any further, and so that's our answer. All right, so these are not the only types of compounds, however. And when we write out these names, as I hinted at before with the sulfate and sulfite, there are different naming systems for different types of compounds. And you have to identify the type of compound first, which is again where a flowchart comes in handy. And of course, just to make everything just even more confusing, there's a lot of things that have common names that throw those conventions out the window. I wouldn't say there's a lot. Well, there are a lot. Okay. Water is one of them, right? We call it water, H2O. Ammonia is another one. And we use their common names instead of their systematic names. So, when it comes to naming an ionic compound, the first step is to identify it as an ionic compound. So we have to remember that anytime you have a metal and one or more nonmetals, remember we made that flowchart previously. We have a metal, nonmetal, and a chemical formula. You can assume the compound is ionic. And compounds that contain NH4 plus are also ionic. So there's the exception to that rule. So you might want to write down a list of rules and then have a sublist of exceptions to those rules. So ionic compounds can be categorized into two types, depending on the metal in the compound. So we have metals that form only one type of ion. That's like our 1A, or group 1A, or group 2A, and our group 3A, right? Those are all metals that form one compound, or form one type of ion. And then we have metals that form more than one type of ion. This would be any of your, or most of your transition metals. Most, right? Because we have some, zinc is one of them that doesn't have multiple ions for the periodic table. So we have aluminum, and if you go just down to the left diagonally, zinc, and then silver also. So aluminum's 3, zinc is 2, silver is +1. I've found that pattern to be helpful in the past. You may not. Okay. So the name of the ion is simply the element name. Metals in groups 1A, 2A, 3A all have charges equal to their group number, like we just mentioned. Zinc and silver are always 2 plus and 1 plus, right, like I mentioned. So you can look at that little, there's this triangle here on the periodic table. And zinc and silver are in there. Mm. Okay, so here's even more. Um, so you can do scandium also is one of those. So you can remember that there's zinc, there's silver, and there's scandium, and those all form single charges. The rest of the transition metals, it's dependent on that individual transition metal. Right, so all metals not in groups 1, 2, A, zinc, or silver, or scandium, as we saw in the previous one, the charges have to be given in some form. And the way we do that is just like in this example, right? So iron 2 plus is iron, and then using Roman numerals 2. Iron 3 plus is iron, and then Roman numeral 3 when we write it out sort of longhand. Here's a list of ions that form more than one. Manganese is not on here, but manganese forms like 3 or 4 different, has different 3 or 4 different charges that it can have. It's one of the wild ones. I'll also make a note that here, this mercury, it is 2 mercury atoms, each with +1. And then we have different names for these as well. So these are the names I think that we'll be using for this class. I say I think. These are the names we'll be using for this class. These are the old forms of the name. So there was always the chromic, which had the higher charge, or chromus, which had the lower charge. Right? So chromic would be +3, chromus would be +2 for chromium, for iron, and for cobalt. But for copper, right, cupric, 2 plus is the higher charge, and copper 1 would be cuprous. But like I said, we'll use Roman numerals. That's more common now. So anions containing a single nonmetal element are named by changing the element name to ide, or IDE. Right, so fluorine becomes fluoride, chlorine becomes chloride, so on and so forth. And these ones have predictable charges from the periodic table, right? So these are fluorine, chlorine, bromine, iodine. Those are all in your 7A. Write this down again, because the more times you see it, the more you're going to remember it. 7A. Oxygen and sulfur are going to be 6A, and nitrogen is 5A. So for this class, all of the ions that we will encounter will contain only 2 ions. Sorry, all of the ionic compounds we'll encounter. A cation and an anion. So the name of the ionic compound is the name of the cation. Oh, I forgot to take a break. Followed by the name of the anion. And the cation is usually the first element, and the exception would be ammonium. And the anion is everything else. So let's name these. We have potassium. K is potassium. And then we have Br, which is bromine. Right? So according to our rules, our cation, because potassium has a positive charge, it's also in group 1A. That stays the same. Potassium have 2 S's? I don't think so. So potassium has it has 2 S's?
Yeah.
Okay. I was always bad at spelling. Potassium stays the same. That's our cation. And then for our anion, we simply change it from bromine to bromide, right? So we drop that Ne and change it to a De, and we get potassium bromide. For this next one, again, we have zinc. So zinc forms a predictable charge. Oh yeah, that's what this one is. So we're looking at metals that form one type of cation. So again, our cation is our positive charge on zinc, negative charge on nitrogen. Zinc would be, check the periodic table. Okay, zinc is the 2. Zinc is a 2 plus, and nitrogen is a 3 minus, right? And then if you're thinking about our crisscross method from before, right, you can see how those are flip-flopped. So we have zinc, 3 zinc, and 2 nitrogen. But our cation stays the same, zinc, and then we change it from nitrogen to nitride. So then if we have a metal that forms more than one type of ion, I think we already mentioned this actually, the charge is determined from the chemical formula of the compound. So you determine the charge on your anion first, and then we know that the sum of all the charges must be 0. For example here, so we have oxygen, and what group is oxygen in? Useful periodic table, oxygen is in 6A. So that means it has a
Negative
2 minus
2.
charge. So then we can say 2 minus times 3. And if you want to write this out as a formula, right, our charge needs to be 0. So that's going to equal whatever the charge is on iron. So I'm just going to write in X for iron, the charge on iron, and that needs to be minus the charge, plus the charge on oxygen. So we have 3 oxygen atoms times a -2 charge. And actually, if you want to take this one step further, right, we have 2 iron atoms, and we want to know the charge on it single. So we have 2x plus -6. We move 6 over to the other side, right? So add 6 to both sides. We get 6 equals 2x. I'm going to go over here. And so 3 equals x. Specifically a positive 3. Right? So you can use this formula to find that charge. So that we know that each of these iron atoms has a +3 charge. So if we want to write this out, it would be iron, 3 in Roman numerals, and then we change it from oxygen, right? Oxygen just, wait, whoa, brain fart there. It's a Y, come on. I swear I'm not having a stroke. We change it from oxygen to oxide. Water.
So in your formula, you did 2x plus -6 because the iron has 2.
Right, because there's 2 irons. And we need to know the charge for a single iron.
Okay. And it has 2 irons in the formula that it gives us right up there.
Right.
Okay.
Yeah, so if you wanted to generalize this a little bit more, we know we want 0. And so then this would be the number of, let's call it C for cation, plus yeah, how do I want to do this here? Number of C times the charge on C, or whatever we're looking for, plus the number of our anion times the charge on the anion. I'm not sure that's super clear, but so we got a few more to practice though. So we have now Pb, which is lead. All right, so we know we're going to have lead. And we know we have oxygen. We know, again, from our previous one, oxygen is going to come up for a lot of these. That's a 2- charge. And so again, if we wanted to do, right, we have 0 equals x with no coefficient because we only have one lead, plus 1, we have one oxygen atom. We could just do this too. We could say 1x times the charge on oxygen, which is a -2. And so we'll get x minus 2 equals 0, and 2 equals x. So then we have lead, Roman numeral 2, oxide. So then for this next one, sulfur. Sulfur is just under oxygen in the periodic table, so this is also a 6A element. So we know it's also going to form a 2- charge. And so we can again use our formula here. 0 equals now 2 coppers, so 2, x being our charge on copper, plus 1 sulfur atom times a -2, because that's the charge on sulfur. And so we can see that we're going to get 0 equals 2x minus 2, and 2 equals 2x, so 1 equals x. Now, if you can do this in your head, you can do it in your head. But always helps on these examples to do everything as step-by-step as possible. So then we'll get copper. And this is the key too here. So we don't need to write the number of copper atoms down. It's just copper 1, and that's a Roman numeral 1. And I'll do this for sulfur because we haven't done a sulfur yet. Right, sulfur turns into sulfide. Again, just changing that suffix to IDE when you're doing a ionic compound. When you're naming an ionic compound, I should say. Let's make sure we circle lead oxide here too. All right. Now, oh, actually, let's take a break here because we missed that break earlier, just like 5 minutes, and then we'll move on to oxyanions. All right, so I'll be right back
Are we
here.
going to go over how to reverse that formulation that we just did? So instead of having the Cu2S, we just are given copper sulfide and then kind of reverse it. Are you going to show us that, or?
I don't think there's an example in here, but
I'm
so
just I'm
yeah, the
just
way you
I'm
would
just
do that
thinking about
then,
our
huh?
I'm just thinking about our nomenclature worksheet. So,
Is there some of that on there? I'm sure.
yeah, first page.
Okay, so let's just real
We can
quick,
do.
right?
Yeah. Okay, go ahead.
So let's say we're just given copper 1 sulfide, right? So we actually know the charge on both of these now, right? We know our copper is going to be +1 charge. Well, sulfide, again, because it's in 6A, is going to be a -2 charge. So when we combine these, we know that sulfide is just sulfur. And
Yeah.
so we're going to always put our metal first, copper, and then, so we have, well, this is very, actually, this is very similar to what we were doing before with the crisscross method, right? So we have copper plus, and we have sulfur 2 minus, and then you just crisscross method to get copper 2 and sulfur. So once you're given one of these names, because we can go over here to lead oxide, right? So lead oxide would be the same thing. I'll come over here, and we're going to have lead 2 oxide. You just have to know that, ide is just oxygen. It's just oxide. And so we're going to lead, Pb. We're given the charge as or not 11, Roman numeral 2, 2 plus. Oxygen, we know, again, because it's a 6A, that it's a 2 minus. And so crisscross method, just remember that when you do this with ionic compounds, we want the formula unit. So this is not the formula unit. We would have to simplify this then to get lead oxide. Cool. So let's yeah, take like 5 minutes. Come back at like 11:45, and we will continue on. I'm gonna swap. I'll leave this up, and I'll just turn my camera off. All right. Let's go. Oxyanions. Oxyanions. So most of our polyatomic anions, like I saw before, there's like cyanide and ammonium. Most of them, though, are oxyanions, which are anions containing oxygen. So a series of oxyanions contains different numbers of oxygen atoms, and they're named systematically. Systems are good. So you only memorize the ones ending in ATE, so like nitrate and sulfate. And then if you know the system that's used for naming them, you can figure out the other names. For example, with one fewer oxygen, then the sulfate is sulfite, like Bud Light has fewer calories. And then you can go further than that. Actually, I think the next page has the thing, but we'll just do it here. You can go one further, one fewer oxygen. You go NO would be hyponitrite. And then if you had SO2, the charges on these stay the same. So this would be hyposulfite. We'll look at those right now. So if there are more than two ions in the series, then the prefix is hypo, meaning less than, and per, meaning more than, are used. So for example, here we have, like I just showed you. I'm going to zoom this in because we have, right, we have our chlorate, which is our base. Put a little arrow pointing to him. That's our base. If we want to remove one oxygen, we do we do chlorite. If we want to remove two oxygens, then we use both chlorite and hypo. And then if we want to add an oxygen, we add per to chlorate. Right? So, yeah, 3. Okay. Same with over here with bromate. If we want to remove one oxygen, we go bromite. And then we do one more oxygen, we have hypobromite. And then for adding one, it's perbromate. Right? So just memorize the base, and then you can get the other ones just using this systematic naming scheme. And you can ignore this about mastering chemistry because we're not doing mastering chemistry. Oh yeah, and you can think of hyper, per, and hyperactive. It's more than. There's a way to remember that. There's a hypodermic needle, which I believe means it's smaller than the like pores in your skin. I'm not sure. That would just be my guess. So we encounter a lot of these polyatomic ions actually in daily life. We have sodium hypochlorite, which is household bleach. It destroys color-causing molecules and kills bacteria. We also have sodium bicarbonate, which is your baking soda. That's a source of carbon dioxide gas if you're not using yeast. We also have calcium carbonate, something like Tums or Alkamints. They neutralize stomach acid to reduce heartburn. And sodium nitrite, which is a preservative for packaged meats. It inhibits the growth of bacteria, especially those bacteria that cause botulism. And botulism is terrible. But you might want to avoid sodium nitrite. It's kind of fallen out of favor recently because of some research that's been done with it and how it can cause cancer potentially. So you can usually buy nitrate free, and when you're nitrate free, that's what it means. Or free of nitrates also. Okay, so let's name these compounds that are containing polyatomic ions. Why am I drawing a blank here? Is there there's just no So manganese is one of our ions that can form multiple charges, right? It's not in the periodic table here. It's not in 1A, it's not in 2A, and it's not in 3A. It's also not zinc or silver or scandium. So it's actually somewhere, it's at 25 there, right before iron. So we know that we're going to need the charge on that ion. So if we remember, we have NO2. You might want to go back and look up on the previous table. But I know NO3 is nitrate. And if we remove one oxygen, we get nitrite, which is what we have here. And because the ion or the charge doesn't change when we remove an oxygen, we know that this has a -1 charge. So again, we can use this equation. 0 equals 1 manganese. We want the charge for that plus 2 nitrites, and they have a -1 charge. So to just do this quickly, 2x. So we're going to have +2 charge for manganese. And so what we're going to do is we're going to write, because we're naming ionic compounds, we don't change the name of the cation, but because it does have multiple charges that it can have, we use Roman numerals to indicate that charge, and then nitrate. We don't change the suffix on we don't change it to nitride, because if we change this to nitride, well, what would be the difference between nitrogen and nitrite? You wouldn't be able to tell. So we keep the suffix for polyatomic ions. Now if we look at cobalt, again looking at our periodic table, if you move 2 over to the right from where we found manganese, you'll find cobalt there. So we also know that cobalt, because it's a transition metal, it's not in groups 1A, 2A, or 3A, it's not silver, it's not zinc, and it's not scandium, so it must have multiple charges. Again, example of what a flowchart would look like, right? We identify first, okay, we have a metal and a nonmetal, so we have an ionic something, or an ionic compound. Now we know that from our metals, we have those with multiple charges and we have those without multiple charges. So we check to see if it's one of the ones with multiple or without multiple charges, I mean. Because it's not in that group, it must be in the other group. So, again, CO3 is carbonate. Probably have to look these up for a while, and that's a 2- charge. And here, you might not even have to do your formula, right? We have 1 carbonate, and we have 1 cobalt. We can just say, okay, well, the charge has to equal 0. And so since one's 2-, the other must be 2+. So we have 2+ for cobalt. Again, ionic compound. So cobalt, because it's one of those with multiple charges possible, we give it its charge here, cobalt 2, carbonate. All right, and again, for polyatomic ions, we're not going to change that suffix when we're naming an ionic compound. So, we've done now ionic compounds, but what if we have 2 nonmetals that are bound together? How do we name those? The first step, of course, is identifying it as a molecular compound. So, right, your flowchart now is going to look like, is it molecular or is it ionic? Well, if we've got 2 nonmetals, we're going to have a molecular compound instead of an ionic one. And then for our molecular compounds, we're going to have a binary or a 2-element molecular compound for this class. And so we have a prefix with the name of the first element and a prefix with the name of the second element plus IDE. So these are kind of the, make sure you don't lose this in here. Prefix and prefix. So we give prefixes to each of the elements to indicate the number of atoms present. And those are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And again, this is one of those things that maybe you've had some familiarity with, or if you know, sort of, I think these are Roman prefixes, then you'll have some idea of what these are, but it might take some time to get used to them. And it would be good to keep a table like this on hand, or, put a post-it note in your textbook. I don't know that this is in there. This looks like a table not made in the textbook, but if there's one in the textbook, right, mark that down. Okay, so if there's only one atom of the first element, right, because we talked about it's going to be prefix, first element, and then we're going to have a prefix, and then we're going to have second plus ide. If the prefix is mono, for the first element, it's normally omitted. So, for example, for carbon dioxide, we remove the mono. We don't say mono carbon dioxide. Again, one of those things that's implied. So, when the prefix ends with a vowel, and the base name starts with a vowel, the first vowel is sometimes dropped. So, dinitrogen monoxide, which is not really a great example, but the prefix is mono, but we don't say monoxide. So you can see that we're dropping this first O on the oxygen, replacing it with the O in mono. So to name some of these compounds, right? So if we're thinking now about our overall flow chart, we have ionic compounds and molecular compounds. Our ionic compounds contain metals. So we look at our molecular compound now and we see that nitrogen, oxygen, where are they on the periodic table? Way over on the right side, those are nonmetals, so molecular compounds. In addition to the context clue that it says naming molecular compounds. So now we just need to remember our prefixes and the names of these atoms or elements. So di is 2. So we're going to have dinitrogen. Oh, this is what I remember. I wanted to do this here. So we can clearly see dinitrogen. And the prefix for 4 is tetra. And this is an example of where we don't drop that first vowel. So the rule was when the prefix ends with a vowel and their element name. Okay, I did it automatically. But I also wanted to do this.
So why isn't this reduced down to NO2?
Good question. Very, very good question. This is a molecular compound. So for ionic compounds, right, so ionic compounds exist as, let me draw it like this, right? We've got all of these, and then they form, I'll draw these ones in between. They form a sort of lattice grid like this for ionic compounds. Molecular compounds aren't like that. So when we do an ionic compound, we're looking for, right, so this is ionic. We're looking for the formula unit. For a molecular compound, consider, we talked about before, H2O. Oh, actually, doesn't really work out the same way. H2O versus H2O2. But molecular compounds work out to individual molecules. So they occur
Oh, I remember.
individually as these units of 2 nitrogens and 4 oxygens.
Okay, so you'd never have a nitrogen connecting to an oxygen unless it's N2O4
for this compound.
for this compound.
So yeah, so N2O4 would be different from NO2. And in fact,
Okay.
NO2 is nitrite.
Dioxide.
Well, this is a polyatomic ion, so it's a little bit different. Uses a
Oh
different naming
gosh.
scheme.
Okay.
So this is like from our previous table. This would be nitrite, which is
Oh
very
yeah.
different from N2O4. Yes. So that's another thing to add to your flowchart, right? If we've got an ionic compound, once you've gotten all the way down to like naming it or to converting the name into a molecular formula or ionic formula, then you need to simplify to the formula unit for ionic compounds, but not for molecular.
Okay. My flowchart is the size of the textbook at this point, so
It's going to be a big flowchart. But here's the
yeah.
thing too, right? You can work on this and optimize it and condense it, and the more that you work on that flowchart, the more you're going to memorize it.
Okay.
Yeah, cool. That's a great question. So, moving on then, right? We have nitrogen again, but we have a single nitrogen. So and we have a single nitrogen, and it's the first element. So we're going to omit mono, and then we have 3 hydrogens. So our prefix for 3 is tri. Hyd. Hydro, right? So it's hydrogen, but we replace the back end with IDE. So trihydride. Okay, so now we've named. This is the last. Let me double think. Let me think about this for a second. I think this is the last group of things that we're naming. I think. So we've named ionic compounds now. We've named molecular compounds. And now we're going to name acids. So when we have acids, we have 2 different kinds of acids. When acids are called acids because when they dissolve in water, they release hydrogen atoms. And so it's not like the acid that you see in the movie, the big vat. Not every acid will melt you. Only some acids. So this is the chemistry definition, not the Hollywood definition. So we categorize these acids into 2 groups. Again, here we go, right? Another flow chart, another decision tree. We have our binary acids, which contain only 2 elements, which are going to be hydrogen and a nonmetal. Again, right? So we can already make a distinction between this and our ionic compounds, because again, no metals. And our oxyacids, which are going to contain hydrogen, a nonmetal, and oxygen. So for our binary acids, the naming scheme is pretty simple. We just add hydro, and we change the end of the nonmetal to ic, and then we add acid at the end with this space here. All right, so HCl is hydrochloric acid, HBr, hydrobromic acid. So to name a couple other ones here. Again, if we're thinking now about our what our flowcharts might look like, we don't have a metal, right? Hydrogen and fluorine. Hydrogen is on the left, but it's at the top. So hydrogen's the exception, right? So we have hydrogen at the top left, but it's not a metal. And then we have fluorine, which we can see is all the way over on the right side in column 7A. And then thinking about this in terms of, okay, is it an acid or is it a molecular compound? We have hydrogen first. So if we have hydrogen first, it's an acid. Hydrogen first, it's an acid. That's always true. If we don't have hydrogen first and you have two nonmetals, then it's a molecular compound. So, according to our chart from the previous slide, to name this compound, we're going to add hydro. Oops, I wanted red. Hydro. And this is all part of the same word here. Hydrofluoric acid. And I'm sorry, I'm bad about when things should be capitalized and when they shouldn't. Nothing in chemistry, unless it's somebody's name or the first word in a sentence, it's all lowercase. Or if it's a periodic, if it's an elemental symbol, right?
And so I'm sorry to just so that AQ is meaning that it's an acid. It's always written like that if it's an acid. That
Oh no, so this this means aqueous. That just means it's in water.
okay.
Yeah. So it doesn't have to do with being an acid because you could have things in solution. So you could have like sodium chloride and you would write it aqueous to show that it's in a water solution. So now again on the second one, we would again, go through our checklist. Do we have a metal? And then this is the way my checklist would go probably. I would look for a metal first, and then I would check to see if the first element is hydrogen. Because if there's no metal and the first element's hydrogen, then we have an acid. If neither of those things are true, then it's a molecular compound. So, hydrogen is not a metal. Oh, but we have hydrogen first, so it's an acid. And if we want to really double check, we know that acids are going to be a hydrogen and a nonmetal for binary acids, a single other nonmetal. And then we can find selenium actually underneath oxygen in column 6A, so we know that's a nonmetal. And this is a good example because, right, we have two hydrogens. But when we write out the acid, we still only write hydro, and that's selenium. So hydroselenic, and I will make this in red too, acid. So we have hydroselenic acid. And to that earlier question, what if we wanted to go in the other direction? If we were given hydroselenic acid, how would we come up with H2SE? And again, we would write, okay, so we know it's hydroselenic acid, we know it's an acid, we know there's going to be hydrogen, so we would say hydrogen, and then we know it's selenic, so we know we have selenium, we have Se, and now we would go to the periodic table because we need to know the charge that selenium has. Since selenium is in 6A, selenium has a 2+ charge. And hydrogen is in column 1A, so we know it has
Isn't it a 2 negative charge?
Nope. Oh yeah, I'm sorry. 2 minus. 2 minus charge. Right, so since it's in 6A, 2 minus charge. Thank you very much. You could do the cross product method here, right? The crisscross method. Or you could just see that this is a +1 charge, this is a -2 charge. So to cancel out our charges, because again, we want our charge to equal 0, we just need 2 hydrogens for our 1 selenium. So if you wanted to go backwards, that's how you would do it. Okay, now we have oxyacids. I said acids. Acids as a whole were our last group. Oxyacids are acids that contain oxyanions. So we talked about our oxyanions earlier. That's things like nitrate, sulfate, sulfite, bromate. It's going to be almost always a nonmetal with oxygen, except for cyanide and ammonium. So when we name these oxyacids, it's going to be things like right, the hydrogen with the nitrate, and then the number of hydrogens is going to be dependent on the charge of the polyatomic ion, or oxyanion. Sorry, the oxyacids are not going to include cyanide and ammonium. So they will always have oxygen. And the way we name these, so you have to know then the ending of your oxyacid. Right, so ite becomes OUS, and ate becomes ic, or IC. And then just add acid after that. Pretty simple. So here's just a table that goes through them. Right, we have oxyanion name as nitrite, so that becomes nitrous acid. Nitrate becomes nitric acid. Sulfite becomes sulfurous acid. Sulfate becomes sulfuric acid. And so again, there's like a convention to the name scheme. So if you know for those polyatomic anions, right, we talked about these, we're adding or removing one oxygen. If you remember sulfate, then you can go say, okay, if I know sulfate is SO4, so this is SO3, it must be sulfite. And then from there, if it's an acid, you know that ITE needs to become OUS. So let's name some oxyacids. So we have here NO2. If we remember our, memorize our polyatomic anions, NO3 minus. This is nitrate. So to remove one oxygen would be NO2 minus. Again, the charges stay the same. Nitrate. Nitrite. So then we know, because it's ITE, that our suffix here is going to change to OUS. So this would be nitrous. And again, I want to use this convention. Right, R, and then the suffix that we're changing in red here, nitrous acid. For our next one, all right, we have ClO4. And I'm not remembering ClO4. So chlorate is ClO3. So we have ClO3. What was the charge on that? 1 minus. So we have 1 minus charge. This is our ATE. Now, think back to that table. If we wanted to add an oxygen, but we're already at ATE, then we need to make it hyper, right? Per. So this is now perchlorate. And with an ATE suffix, that's going to become IC. So we're going to just have, again, I'm bad with these capitals. I'm never going to mark you off for capitalizing those kind of things. It's just if you type it. We're going to do, per. Let me make this neater. Perchloric acid. Just to reiterate here, yeah, AQ just means aqueous, so in water. And now too, right, you can sort of reverse this process if we wanted to turn these back into names for given, and I'll zoom so we don't just cheat. Perchloric acid. We know it's an acid, so we're going to have a hydrogen, at least one. We know per adds an oxygen. We know that chloric the ic becomes ATE. And so really you have to kind of, especially for these oxyacids, you have to decode the name a little bit. We know that chlor 8 is going to be ClO3 minus. And we have a per, so then we're going to take per and add an oxygen. And now again, we have hydrogen has a plus charge, ClO4 minus. And you could crisscross method or just see here that our positive charge is going to cancel out our negative charge. And we just have HClO4. Cool. I'm going to try and be better about giving you a second after I write something to copy that down. If you're watching the YouTube video, you can just pause. But now we have sort of the flowchart of all flowcharts, at least for this. Turn my webcam here off too to get it out of the way. So, if we're naming anything, we want to go through and do these checks, right? So we'll check first, do we have a metal? And then do we have a hydrogen? And then, okay, maybe it's nonmetals only. And then from there, we pick one of these trees to move down, and we answer every question along the way. And that will give you the naming scheme for each of these ions. I know it looks like a lot, and it kind of is. But this is why there are so many homework problems, so you can practice them over and over and over and over again, so you don't need to look at these tables, these flowcharts every time. So let's move on. I think there's a few more examples here. Just an example of how we might use the flowchart. So let's look at carbon monoxide, which I guess I kind of gave away a little bit. But let's go over here. Let's see. Okay, so we have CO. Do we have a metal? No. Carbon and oxygen. I'll pop the periodic table up for a second. Carbon, oxygen, they're together over on the right side. So we've got nonmetals only. There's no hydrogen. So then we just use carbon. We have one carbon, but we drop the mono prefix. Then we do, so this would be mono, right? Carbon. And then mono, because one oxygen. And then we'll do oxide, because we drop the ending of the second element and change it to IDE. Oh, I guess I'll leave that for a second. All right. I'm going to erase it. And then, so you can see how then you could do that for all of these. And I would recommend, like, do it. You know, take these and go through them and see, work through the flowchart, follow through the flowchart, and get a feel for it. Especially when you have the answers right there. This is the last thing. So we have this thing called a formula mass. And it's the mass of a molecule, or a formula unit if we're talking about ionic compounds, right? So for any compound, the formula mass is the sum of the atomic masses of all the atoms in its chemical formula. Is there an example here? There's an example here, okay? So we just use the number of atoms of the first element in the chemical formula times its atomic mass, not its atomic number, its atomic mass. And then we take the number of atoms of the second element and multiply it by the atomic mass of the second element. And then we add these all together. And that goes on for as many elements are in the formula. So let's take a look at this example. I don't think the periodic table that I grabbed does not have the formula masses. Okay, I'll just have to look them up. So we have nitrogen, right? Dinitrogen monoxide, also laughing gas. So we want the atomic mass of nitrogen and the atomic mass of oxygen. I know oxygen is like 18.01. This is actually, I don't know if I should tell you this, but Siri's pretty good at doing this. Nitrogen mass, I believe nitrogen is 14. Yep. 14.0067. And then oxygen mass. Oh, it's 16. What? Oh, water is 18. 15.999. And then you could say U for atomic mass units. Okay, so we're going to take, remember from our formula previously, the number of atoms in the first element and the number of atoms in the first element times its atomic mass, number of atoms in the second element times its atomic mass, and then we'll add those together. So we have 2 nitrogens, so 2 times 14.0067 plus 1 oxygen, right? So we can do, just for the sake of clarity, we'll write 1 times 15.999. 2 times 14.0067 equals that, plus, 1 times 15.99 is going to be 15.999. So our answer then would be 44.0124. Actually, again, always paying attention to significant figures, because we're adding. We use the fewest number of decimal places. So 0.999 is one fewer decimal place. At least one fewer decimal place. More after we multiply, maybe. Oh no, just one fewer decimal place. So then we're going to actually use this as our final answer. So that's atomic mass units. AMU, or can also be abbreviated to U. Okay. Are there any questions about Chapter 5?
When are you going to post this recording? Because I need to watch it about 87 more times to be able to actually understand any of this, especially the second half.
It's understandable. Okay, oh, I should have done this too. We'll do it right now. There's the YouTube recording. There's also a Zoom recording. The Zoom recording comes up much faster because I have to drive to my brother's house to upload the YouTube videos, because they're about, depending on how long the class goes, 8 gigabytes. On my internet, it would take a full day to upload. So let's see here. Not League. Okay. So here's here's the canvas. I've been posting an announcement every day. Here we go. Yep. See, Chapter 4 lecture is live on Zoom. So if you check your announcements, you'll just have to copy and paste this recording. And you can access, and then there's also a transcript here. This is the audio transcript, which is not going to be super great because chemistry terms don't get translated very well. So I will, as soon as we're done here, I'm going to drive over to my brother's house, upload the video. And then YouTube takes a long time to process that as well. But I will post the link as soon as it's up, and then you can just kind of check back every 15 minutes or so to see if it's up or if it's ready. The link also does get posted to Discord. Okay, I can stick around. And we could do some more problems. I pulled at least one. I don't remember what the problem was. This is from the back of the book. Oh, right. Okay, so we have carbon tetrachloride, and it's decomposed into its constituent elements. One sample produces 32 grams of carbon and 373 grams of chlorine. The other sample produces 12 grams of carbon, 12.3, and 112 grams of chlorine. Are these results consistent with the law of constant composition? So the thing we have to remember with the law of constant composition is that, if you think about the name of the law, the composition should be constant everywhere. So if we work out the ratio of these, and oftentimes that's like the goal when you're comparing two things, is to get a ratio. We'll do 373 grams of chlorine divided by, and this is for sample 1 in my terrible handwriting, divided by 32.4 grams of carbon. And we want to know, is this equal to sample 2, which is 112 grams of chlorine divided by 12.3 grams of carbon. So 373 divided by 32.4 is going to be 11.5. Do 5.1. And then we'll do 112 divided by 12.3. Oh, 9.11. So these ratios are pretty different. We would say that these results are not consistent with the law of constant composition, right? Because the ratios are not the same. So in a real world type scenario, we'd probably conclude that one of those things is not carbon tetrachloride. I didn't grab any other questions. I did, however, and this is probably more interesting, was going to go over some of the most missed questions from the exam. Let me just pull it up here.
We maybe just do one or so off of the nomenclature worksheet. So like, right, the cation formula, anion formula, compound formula.
Yeah, let me, I'll just do a blank note here. And then I will go to, let me pull up that worksheet. Modules, nomenclature worksheet. Oh, good. The nomenclature worksheet does have that spreadsheet on there too. Okay. Was there a particular question?
Well, I mean, I don't know. I just don't.
Let's do just like the first couple from, at least the first couple from the ones that have a lot, and then maybe just like. Oh, you can't see this. I'm looking at the worksheet right now. I'll write them down. Let's see. The first word is the name of the cation. Second word, name of the anion. Okay. So just what it's asking for.
Yeah. So I mean, like, so the first aluminum sulfate, the cation formula, has 3 charges on aluminum. So, right? I mean, do we write Al3 plus or?
Yeah. So then we'd have our, right. This will be the cation, and then I'll do the anion. So then this would just be Al3 plus. And then for sulfate, right, that's one of our ATE Oxyanions, SO4, 2 minus. And then for the compound, right, would now be the combination of these two accounting for their different charges. So again, using the cross product method, to avoid making things too messy, maybe I'll just do like this. All right, we're going to put this here. We're going to do red. It's going to go over here. So we're going to have Al2. And then, of course, in parentheses, because we have a polyatomic, 3.
Just doing crisscross.
Mm-hmm. Just crisscross those.
2 times 3 from the aluminum.
So let's just do the next one then. Yeah, that'll be a good one. So this is one of those exceptions. Ammonium carbonate. So this is the exception to, is there a metal it's ionic? If it's ammonium, ammonium is the only other thing that you can have that sort of counts as a metal. Counts as. So when we do ammonium carbonate, if NH4 plus is ammonium, carbonate is one of those ATE polyatomic ions that you should memorize. That's CO3, 2 minus. Right? So again, just the crisscross.
We'll have NH4, 2. NH4 in parentheses, then 2, and then CO3 in parentheses. Oh wait, no, there's nothing over there, so it's just CO3.
Yep. Yeah, just CO3 for that one.
And then like on the ones with the Roman numerals, so that's telling us chromium is on the first one that has a 2 charge.
Mm-hmm. Yep. And then you just have to make sure that when you write the compound formula, that you are canceling all the charges, right? That's what the crisscross method does. It's just a quick and easy way to make sure your charges are going to cancel.
Okay. So it would be on the chromium 2 cyanide, it'd be Cr2 plus for the cation,
Mm-hmm.
and then chromium, cyanide would be it's Cn negative 1 negative.
Mm-hmm.
Okay, so then the compound formula would be Cr, just plain Cr, and then Cn2.
Mm-hmm. In parentheses.
So the Cn in parentheses and then times 2 because it's a compound, right?
Yep. Yeah. Yeah, because it's a polyatomic.
Cool. Okay, I get it.
Yeah. Ionic compounds contain 2 ions, a cation, anion. So yeah, for like part 2 there, just kind of the same thing. You're just starting with the, oh, I see, you're starting with, it's the inverse, right? So this is what you were talking about, going from the formula, or no, the previous one was going from the name to the formula. That's what you were talking about. And then from the formula to the name is what we did a lot of. But we can go over one or
The
two.
cation name first would be potassium for the K, right? So potassium with 2 S's. And then anion name would be bromine, but let's see, would it just be bromine or?
I think it just wants the anion name, right? And then you're going to change it when you make it a compound. So it's just the name of the anion.
Bromine. Potassium bromide.
Mm-hmm. See if there's any other ones that are kind of tricky.
Maybe let's do the aluminum one down there on the bottom because I feel like that's going to have some sort of parentheses.
Ah, Sure, yeah.
I don't know. So aluminum, and then OH.
Let's say to write that. Oh, it just says to write their name. But
Is that OH? Would that be like hydroxide or something? Or
yeah, hydroxide. Hydroxide. Um, so sodium hydroxide is Li.
okay, making.
Also, drain cleaner. Sodium hydroxide.
So the compound name would be.
I think this one's just aluminum hydroxide.
So there's no crisscross 3 and everything, or?
Well, we're just writing the compound name, right?
Oh yeah, compound name, aluminum. So, well, no, so it wouldn't be aluminum parentheses Roman numeral 3 hydroxide.
Ah, well, aluminum is one of our special case transition metals.
Okay.
Well, it's not even in the transition metals, actually. It's in column 3A.
So it's always a +3, so you don't need to specify.
Right. Yeah,
Okay.
and that's why that triangle can be helpful, because you get
So
right,
then the one right
aluminum.
above that is going to have parentheses, right? Because it's iron. Is that a special one, or is iron? Because iron can change, right?
Iron can change, yeah. So you have
Okay.
the special ones are going to be aluminum, which is like aluminum's in 3A. So aluminum, gallium, this is just how they are on the periodic table, right? Indium, also going to be 3 plus. And then if you go to the left, zinc is a 2 plus, and then silver, leave a blank here. Silver is just 1 plus. And so that's why you get this. That's why that triangle is drawn on the periodic table, because you can use aluminum and then sort of draw this triangle in your mind and find those ones that have set charges. Let me see if cadmium.
Cadmium is 2, right? Because it's between the indium and the silver.
So I would assume. Yes, it's only the +2. So cadmium's in there too. So CD is also 2 plus.
Okay.
So you have this whole triangle there of metals that form only a single ion, and then scandium, which was over on the left, was also only a 3 plus charge.
Okay. So on our question sheet here, the iron 2O oxygen 3 cation name iron, anion name oxygen, but then the compound name, do we just do the crisscross? So then it's iron Roman numeral 3 oxygen.
Let's see, sorry. Yes.
Okay, so there's no trick associated with that.
No, just yeah, make sure you've got the right charges. Oh,
Yeah,
oh wait,
so I
hold
mean,
on,
so
hold
is
on.
there just a crisscross?
Because yeah, you can just use the crisscross like that, right? So it's iron 3. Because if you were to do the math there,
We know oxygen is a -2.
exactly, right? So you know oxygen is 2 minus, and then there's 3 of them. So it's going to be the -6. And this is why we worked out the math on that one. And you have 2 irons. So to cancel out that -6 charge,
Has to be 3.
yeah, this has to be 2 times what? And x equals 3. So yeah, just the crisscross method is enough, though, to tell you that iron is going to be a 3 charge, 3 plus. Okay. So you would write it, yeah. Iron 3. I usually leave the tops and bottoms off the Roman numerals. Yeah, so when you're looking for those, these are the special ones. There's that triangle
always the same.
and the scandium. Always the same.
Okay. Well, I've got a super big headache now, so hopefully I can and I've got 87 papers in front of me, so hopefully I can sort these out.
Take a couple ibuprofen.
Yeah, really.
Take a couple ibuprofen. Take a nap.
Yeah.
Go on a walk, and then
Yeah.
come back.
Seriously.
Yeah, and you got the weekend, and I mean, obviously you don't want to be working too much on the weekends because your brain needs a break. But it's a 3-day weekend.
Okay. Yeah, well, the homework in this thing, I think they're due tomorrow anyway, so I'm gonna either
they are
bang
due
it out today or.
Yeah. But if you get it done today, you'll have to do it on Monday.
Exactly.
And then there's no assignments on Monday, so there's nothing due Tuesday either.
Oh, really? Oh, yeah, because it's a day off, right?
Yeah, Memorial Day. So there's not another assignment due after this one being due Saturday until next Wednesday.
Okay, cool.
Just kind of get a huge break there, or time to work ahead.
Yeah, no, I always prefer to work ahead. I don't want to be up against the.
Yeah, you don't want to be there with this class.
Yeah.
I'm going to stop the recording.
Okay.
The recording has stopped.